Hello everyone, and welcome back. So, this time we're going to be talking through the second method of solving problems, which is the method of sections. So let's go through the procedure and then we'll try out an example problem. So first off, we have to calculate the reactions for the whole truss using a free body diagram for the entire truss. That means getting rid of all of our pin supports and our rolling support and replacing those with forces. And then we're going to figure out a portion of the truss that we want to actually solve for, making sure we cut through no more than 3 members. Reason that we had that number 3 there is because with the method of sections, you get all 3 equilibrium equations. Some of the forces in the x are horizontal, some of the forces in the y are vertical, and some of the moments about a particular point. So if you cut through more than 3 members, you can't actually solve it. You'll be stuck. And we use our equilibrium equations to solve. And if we want to, we keep moving around until we find everything we need to. Now, if you're really worried about this, you can verify your questions by, going back through, making sure that everything actually works out. So once you've solved some of the forces in the vertical direction, the horizontal direction, or some of the moments around a particular point, and see if it works. So let's try an example to show this in practice because it's not always easy to see. Now, you see there's a whole bunch of forces. We're not going to get all of them. All it asks for is the forces at BD, so that's from B to D right here, CD, okay, and CE. Now, that seems like there's a pretty nice spot here to cut through. But we're not there yet. We'll get there eventually. First, what do we have to do? We have to solve for our reaction forces. So let's draw a free body diagram. We replaced all of those forces with a reaction force. And we went ahead and showed what the slope of our triangle was. And we get that just from the geometry. Now we have we have 3 equations and we have 1, 2, 3 unknowns. It should be enough for us to solve. And so what I'm going to do is I'm going to take this moments around point J to begin with. You're like, wait a minute, why point J? There's a very good reason for this, and I guess I'll go ahead and try to explain why point J. You don't have to realize this, but in the end we're going to be cutting through here. When we cut, we get rid of half of this. So this entire side is probably going to disappear because it's the bigger side. This is a nice small side. It'll be easier for us to solve with. Less drawing. So we don't actually need to solve for this reaction force. We don't need it in the end because we're solving for these internal forces. We'll only need to know the forces on this side. So we do that. And might be a second thing we might be asking is, well, what about this one? Well, it doesn't actually cause a moment about that point because its line of action goes through that point. So we look at it. So we have 2400, and that is going to be counterclockwise, which is good, so that's positive. And that will be times 12. We have 4000 times 24, also positive. We have 1600 times 36, also positive. And then we have finally our vertical force at A times 48, which will be negative. So all 3 of these are positive, the rest are negative. From that we get our vertical force is 3,800 pounds. Now the second question for you is, do you see any other horizontal forces? Any horizontal forces at all being applied to our particular truss here? The answer? No, you don't. So if we wanted to, we could just say that the horizontal force is 0. Now I went ahead and solved for our JV, which is the reaction force at J in the vertical direction. And you can do that. You didn't actually have to. So if you want to check yourself or practice doing a moment, you can go ahead and use this if you wish. We're going to see soon that we won't actually need that force. So now we're going to cut through the truss right there and draw a new free body diagram. As you can see, everything to the right of that free body diagram ceases to exist. It's no longer there. And even though we draw these forces at the end of this line, it's usually better to imagine that they're applying at this joint. That will make it a little bit easier when you're trying to figure out distances for moments and things of that nature. So we have to write some equilibrium equations so we can solve. Now, if I'm looking at this, there's various ways I might solve it. For one, there's only one unknown that's going in the vertical direction, so I can probably solve that pretty easily. There's two unknowns around this point, so we'll take some unknowns around that point. That would help me solve for an unknown. There's lots of ways to go about it. So I'm going to go with the vertical forces first, because that jumped out to me first. So I have force CD, and it's going down, which is negative, and 3/5 of it's negative, because with using this slope triangle, I'm going to get the vertical component by taking the vertical component of my slope triangle over the hypotenuse. And I have 1,600 pounds also pointing down, and I have 3,800 pounds pointing up. If I solve for that force CD is going to be 3,667 pounds. Okay, that leaves me with two unknowns, and I've still got two equations. Shouldn't be an issue. Now I'm going to take the sum of moments at C. I could have done it at other point now because I have, I've gotten rid of that one unknown. But if I did it around point B, I would still have to take into account the horizontal component of that force. I don't want to do that. That's just more work on me. So instead of doing that, I'm going to make it easier myself and just take the sum of moments around this point. So it doesn't even have a component. So when I do this, I have several different things acting on it. First off, the 600 pounds, it also doesn't actually cause a force because it's going through that line of action, which means I have force BD, which is my unknown, and that's going to be, that will be counterclockwise, which is positive, times 9 feet, good. And I have this other one right here, which is clockwise, so that one is negative. I try to keep the sign convention. If I switch it on you, I apologize, but usually counterclockwise positive, clockwise negative. And each of these are multiplied by their particular perpendicular force to that line of action. When I solve, BD is 5,067. And once again, I ask why C. That's just so I can get rid of that extra unknown and not have to worry about it when I'm doing my moments. Now, I have one component left, which is this vertical component right here. Sorry, that's not one. This one right here, CE. I want to solve for it. So I'll use some of the forces in the horizontal direction. And I know BD, so we're good here. I know CD and can therefore find the horizontal component, which is just the horizontal component of the slope triangle over the hypotenuse, times that. And then I have CE. So C is pointed to the right, that's positive. Everything else is pointed to the left, which is negative. And I solve and get that CE is equal to 8,000 pounds. And look at that, we're done. We can completely, sorry, I jumped too far. We can completely forget the rest of our truss. I'll just jump back a little bit so you can see that. All these forces didn't matter. This reaction force did not matter. We were to solve it using method of sections. So this is one bonus to the method of sections. You don't have to work your way slowly to the point you want. You can just jump straight there and solve. So thank you for listening. I hope this helps you. And I'll see you all next time. Bye-bye.